Hello everyone and welcome to part 4 of mobile equipment power. So before we start the new parts of this chapter, which are the last parts of chapter, I guess 6, I want to have a quick review on parts 1, 2, and 3. So we want to review what we have learned so far in this chapter. So technically in this chapter, we're talking about two different types of forces. The first type are the forces that resist against the equipment to move, okay? In other words, the equipment has to overcome these forces to move. So these forces are two, or these resistant forces are two. Number one is the rolling resistance, and number two is the grade resistance. And if you remember, rolling resistance is the resistance against, the wheels. If it is moving on a level surface, it means you're not considering any grade impact. You're moving on a level surface and you're moving at a constant speed. It means your speed is not changing. So speed is not a factor. In that case, the resistance that is applied from the surface to the tires, or where the tires touch the surface, that is called the rolling resistance. And the second one was the grade resistance. So obviously when you're going up a hill, there is some resistance to pull the machine up, okay? And the term total resistance addresses the summation of the two forces I just talked about. So rolling resistance plus grade resistance will give us the total resistance. Okay, on the other side, we will have the forces that the machine generates, okay? So the machine generates torque, generates rim pull and drawbar pull that we discussed in part 3 of this chapter. So obviously, to make the machine move, the forces that are generated by the machine should overcome the resisting forces, okay? And then only the machine can move. In other words, the usable power of the machine is the power the machine generates minus the power it needs to overcome the resisting forces, okay? It means not all the power that the machine generates is useful, because a part of it should be consumed to overcome existing resistance against its movement. Okay, with that introduction, so required power is the power needed to overcome resisting forces. This is what I just said. The two important resisting forces are the rolling and grade resistance, and the total resistance is the summation of rolling and grade. So rolling resistance was the wheel resistance or track resistance. I'm using this word a lot. So rolling resistance is the resistance of a level surface at a constant velocity or constant speed. If you remember, we talked about what rolling resistance depend on. So we listed some factors that could lower or could increase the rolling resistance. And if you remember, we said that the more stable is the surface of the road, and which is achievable by compacting the soil. So the more stable it is, there will be less rolling resistance against the movement of the equipment. All right, so on the mathematical part and the computation part, we said that the rolling resistance could be found in two cases. Case one is when the tire penetration is unknown. So we don't know the tire penetration. In that case, we simply use this equation, and in which P is the total tension in tow cable, which comes in pounds, and W is the gross weight of the mobile vehicle, okay? So obviously, there is an inverse relationship between the rolling resistance and the weight of the vehicle. So the second case was when the tire penetration is known, because tire penetration has a huge impact on how much rolling resistance you will get. Okay, the more you penetrate, the more the soil penetrates into the tire penetrates into the soil. It will be more difficult for the tire to rotate or to roll. Okay, this means the rolling resistance will be higher. Okay, so the penetration of the tire, if that is known, we can find the rolling resistance using this equation. Okay, where RR is the rolling resistance, TP is the tire penetration. As you see, it is directly related with the tire penetration. The more it is, the more will be the rolling resistance. Okay, computing rolling resistance for grades lower than 10%. If you remember, we said that we present the grades in construction with percentages, not with other types of measurements. So if that is given, let me get my pen in here. Okay, so I get a red pen. Yeah, so for grades lower than 10%, the rolling resistance will be 20 times, okay, 20 pound per US ton, okay, which is the weight of the vehicle, multiplied by the grade percent, or the grade, the grade percent, or the gradient. So it means it is directly related to the weight of the machine. Okay, so equivalent gradient for rolling resistance. If you remember, we said the total resistance is the summation of rolling and grade resistance. So if you want to sum them up, or if you want to add them with one another, they should be of the same type. Okay, if one of them, well, obviously grade resistance comes in percentages, but rolling resistance could come in pounds. Okay, so we need to convert rolling resistance in such a way that it could be added or subtracted to or from the grade resistance. And the minus and the plus and minus signs, you know that plus is for for going up, and minus is for going down. So total resistance will be less if you are going down the hill. You will be needing less power, less force to move your vehicle. That makes sense, right? All right, so we can convert the rolling resistance to an equivalent gradient, if you remember. For that, rolling resistance, which was expressed in pound per US tons, must be divided by 20. And that's an empirical, it's a good estimate. It gives us a good estimate of the equivalent grade resistance. So again, what we are technically doing is that we are converting the rolling resistance into a grade percent so that it could be added with the grade resistance to find the total resistance. Yeah, so we also talked about, this completes the resisting forces. Now, there are some forces that the machine generates, okay? First of all, the first one in the list was the torque, okay? Torque usually comes from, is generated when you rotate an object, with different speeds, and it is directly related to how fast that object is rotating. So, the speed of rotation could be measured with revolutions per minute, or RPM. And if you have the RPM, the torque will be, we have a constant. This number is the constant. We will always see that. And with if you divide it by revolutions per minute and then multiply it by the horsepower, you will find the torque. So torque and horsepower are, directly related. Torque and RPM, or the speed of the rotation, are inversely related to one another. Also, by having, the horsepower, you can find the torque, and by having the torque, you can find the horsepower if you play with the formula. So, we also talked about rim pull. If you remember, rim pull was the force that the tires could apply on the surface and make the machine move. So it is directly related with the power that the machine is generating and the efficiency. And we said the efficiency usually ranges between 0.8 to 0.85, and that should be divided by the speed. It means the faster you move, the less rim pull you will get. They are inversely related to one another. Yeah, like I said, it usually ranges from 0.80 to 0.85 if it is not given to us. Another force that we talked about is the drawbar pull, the power of the machine to drag or to draw a load, and we talked about it. So how does the grade impact the draw pull? So the grade is related to drawbar, right? If you're dragging a load on a level surface, you probably will need less power compared with when you're dragging it up a hill, okay? So, but how exactly are they related? So here is the estimate. If a crawler tractor, so we're talking about a crawler tractor, tows a load up a slope, its drawbar pull will be reduced by 20%. It means when we say its drawbar pull will be reduced, it means it will have less power. The force that it can generate will be less. It will be reduced by 20 pounds for each ton of weight for every 1% of slope, okay? So obviously if it is 5%, so it will lose more power. If it is, so, and then 20 must be multiplied by the weight, which is measured in tons. For example, if your vehicle is 15 tons, and if you're going up a grade with 5%, then 20 must be multiplied by 15, and then it should be multiplied by 5. So 20 times 15 times 5 will give you the drawbar pull, okay? So obviously on a level surface, the drawbar pull, the usable drawbar pull will be a lot more compared with, with a positive slope. And the unit of measurement for the drawbar pull is pounds. So we also talked about coefficient of traction. Coefficient of traction talks about, so when you want to find the usable force, you should find a coefficient of traction, and then, you should multiply it by the weight on powered running gear, okay? So the coefficient of traction is usually given to us, and it depends on the type of the surface, okay? So as you can see, for a dry surface compared with a wet surface, so if you compare this guy, if my pen writes, okay, this guy with this guy, as you can see, the coefficient of traction is higher. It means the usable force is higher in a dry surface. That's why in construction we do not like wet surfaces, because the coefficient of traction will be lower and the usable force in a wet surface will obviously be lower. All right, that actually that completes our review on parts 1, 2, and 3. And now let's get started with an important part, which are performance charts. So what is a performance chart? The performance chart is a graphical representation of the power and the corresponding speed. So usually the manufacturer provides you with a chart, and by which you can easily find that for every amount of power, how much speed you can get from this machine, okay? Where can we find performance charts? Like I said, equipment manufacturers usually will give it to us, or if you rent an equipment, it is usually provided by the company you rent from. What are performance charts used for? So why is the speed so important for us? Because you want to know how fast you can get the job done. That determines your schedule, and your schedule determines your project duration, okay? So you want to know how fast your vehicle can move on the surface, okay? That's why we're interested in finding the speed of vehicles. And for that, we will need a performance chart. So an estimator or planner will use a performance chart to find the speed, the productivity, and to develop a schedule accordingly. How is the load condition stated? So the load condition could be stated in two different types of rim pull and drawbar pull. How are the drawbar pull or rim pull and speed related? Obviously, they have an inverse relationship with the speed. So if you are towing a car with your car, faster you move, your car can generate a less rim pull, okay? Or sorry, a drawbar pull. And so in order to create more force by your equipment, you have to go more slowly. That's the very simple, concept, which is understandable, right? The slower you move, the more powerful your equipment will be. All right. So this is the first chart that we will discuss, rim pull performance chart. You might think, oh, there's too much information in this chart, but actually it's very straightforward to use it. So I tried to put it in an example or a question. What speed would this machine travel if the rim pull required to overcome the total resistance is 2,900 pounds, okay? So first of all, there are different types of information given to us. In this example, you are not working with the total resistance, okay? So total resistance is not known. We will use the right side of the chart. This side and this side are not used here. We just use this part and this part, okay? The left side and the bottom side of the chart. So the first piece of information that is given to us is the rim pull, and that is 2,900. So it is in pounds, so it is important that first you need to check if it is in kilograms or it is in pounds. In this example, they have given it to us in pounds. So this is the column we will be working with, the one that represents the rim pull in pounds. All right, so what was the number? The magic number we have is 2,900, so it's pretty close to number 3, because so this is multiplied by 1,000. So when you're saying 3, it means 3,000. So 2,900 will be slightly before the number 3 on the vertical axis, which is on the left side. Okay, so we found this number so far, and now if you draw a horizontal line until that horizontal line intersects with one of the curves, okay? So it will intersect with the curve of the 8th gear, okay? And now, so this is the intersecting point, and if you go down from here, the number you will find is 30, okay? That's as easy as this. So you first find a rimple, this is number 1, and then you go to the right hand side until that horizontal line intersects with one of these curves, okay? Here it intersected with the 8th gear, okay? So then you draw a vertical line from the intersection to the horizontal axis on the bottom, and then you could find the speed in 2 different measurements of mile per hour or kilometer per hour. So here are the explanations if you need to do it later at home. I mean, if you want to review it later using the slides, I mean, without the video, you could read the text. All right, so determining machine speed using a rimple performance chart. So what did we do in the previous example? We actually found, we're still finding, we're trying to find the speed on a rimple chart. But what happened in the previous example? So let me bring up another example. If, let's say, the rimple was, instead of 2,900, it was 5,000 pounds, okay? Then what would happen? So on the vertical axis, we need to find number 5, which represents 5,000 pounds. And okay. So let me make a better example. 15,000, okay? 15,000 pounds. So 15,000 pounds is here, okay? So if you want to draw a horizontal line, it will intersect 3 different gears. So what is the speed? What will be the speed? Which of the intersections should we use? This slide is explaining this issue. So sometimes, and I believe in fact often, not sometimes, where sometimes the horizontal line from power equipment will intersect the gear range curve at 2 different points, right? For example, here, okay? Or for example, here. It could intersect, or in more than one, in more than one intersection. So for most of them, that is the case. Actually, anything that is above this line, if you draw a horizontal line, it is going to intersect with more than a single line, with more than a single curve. So what should you do in this case? Here is the answer. If the required rimple is less than what was needed for the previous stretch of the haul road, and what does that mean? Previous stretch of the haul road. It means you should compare the rimple you find, okay? So you have 3 different rimples here. And you're talking about, a haul road which could have different, grades or different conditions. And so you probably will need, you obviously will need different rimple forces, okay? So you should compare the number you find here with the previous number, with the number the effective rimple in the previous section of the road. You compare the 2 values to one another. If the required rimple here is less than what was needed for the previous, for example, in the previous section, it was the grade was steeper, okay? Now it is like this, okay? So you probably will need a lower ripple effect. Then use the higher gear and speed. Okay, so if it intersects more than one gear, for example, if it intersects this, this, and this, so if it is intersecting more than one gear, you go ahead and select the higher gear and the corresponding speed. And vice versa. If the required ripple is greater than the need on the previous stretch of haul road, use the lower grade and the lower corresponding speed. So this is a very important point, and in the exercises, in the problems of at the end of this chapter, you will need this. You will need to know this to solve some of the problems. So once again, you should compare the speeds you get here with the speeds, with the ripple you had in the previous section. And then based on if it is increasing or decreasing, you select the highest gear and its corresponding speed, or the lowest gear and its corresponding speed. Okay. Drawbar pole performance chart is easier actually to understand and to follow. Well, it doesn't mean the previous one was difficult, but this is even easier. So power required for a certain application, here's an example. Let's say it is 25,000 pounds. Okay, so you're talking about pounds, and you're not talking about, you're not talking about kilograms. Okay, I'm sorry. Let's go here. Yeah, you're talking about pounds and not kilograms. If I can move this guy somehow. Yeah. Okay. All right. 25,000. Okay. Okay. Unmute. 25,000 pounds is right over here, right? The pounds is this column, and 25,000 would be here. Okay. Now, what speed would this machine travel efficiently in first gear? So, in solving these problems, it's important to consider which gear you are using. Is it the first gear? Is it the second gear? Or the third? And accordingly, you would select the corresponding curve. Okay. So here you're using your first gear. So it is as simple as this. Step one, locate the $25,000 pounds, which you already did. Move horizontally across the chart and see where your horizontal line intersects with the curve. Okay, so it should be given to us that with what gear we are moving. Okay, so if you're moving with the first grade, so 25,000 intersects with first gear here, and then you draw a vertical line, okay, until you intersect with the speed axis, whether it is mile per hour or kilometer per hour, then you could find the corresponding speed. So as you can see, it is very slow, less than 2 miles per hour, or to be precise, 1.4 mile per hour. Now, what speed would this machine travel efficiently in second gear? So if you are moving with the second gear, you should use this. You should use this curve. And again, you would move, okay? You would move, so the second gear is this guy, okay? And only 1 mile per hour. Okay, so this is the first gear intersect with first gear here, 1.4, and the second gear is this guy. Oh yeah, this is the second gear. Okay, so you intersect right over here. Okay, and the corresponding speed will be 1 mile per hour. Super slow, right? Okay, now determine machine speed when total resistance is known. Remember I told you there's a lot of information in this chart, and in the previous example you would use the RIMPL, this guy, you would use the RIMPL and to find the speed. Now here we want to use the total resistance, okay, and the gross weight. This is gross weight of the vehicle. Having those two pieces of information, we want to find the speed of the vehicle. There are two more steps here, okay? The first thing you need to know, you need to find on this chart is the grade percent, okay? So let's say the grade is, you're working on a 20% grade, okay? So 20% is right here. And let's say the gross weight of the vehicle is 100, okay, is 100,000 pounds. 100,000 pounds. That would be, so this is the pound. Remember not to confuse the kilogram and pound. Here it is 100,000 pounds. So this is the number we will be using. Okay, so the first thing you need to do is to find where that diagonal grade line will intersect the vertical line that you draw here. Okay, so the 20% will intersect at this point. Okay, then you would go to the left. You would draw another horizontal line. Okay, so from here you do a horizontal line and find the corresponding gear, and then from there you could find the speed. If you go down, you would find the speed. So it would be close to 5 miles per hour in this specific example. As you saw, we did not work with the RIMPL. Okay, when the grade resistance is given to us and you want to find the speed, first thing you need to know or you need to do is to find, the corresponding diagonal line, and then the gross weight of the car, and then draw a vertical line with that, draw a vertical line and see where it would intersect with this line, okay? And the intersection, you need to draw another horizontal line and see where it intersects the gear curve. Once you find that intersection, you would now draw a vertical line again, okay? And this will show you the speed of the vehicle. So this is number 1, this is number 2, number 3, and number 4. Okay, and now the explanations. First, ensure the engine, gear ratio, and tire size of the proposed machines are the same as those for the machine identified in the chart. Yeah, remember this. Well, in this class, this is the only chart we're working with, but in the real world, you might have, tons of these charts, and each one is for a different piece of equipment, so it's important to find the right chart for your computations. That's the first step. So it could be the gross weight of the vehicle should be based on when it is empty or when it is loaded. The empty weight is the operating weight, and of course it includes the coolants, the lubricants, full fuel tanks, and the operator. Okay, So it does not mean that you should not consider the weight of the operator. No, it is the operating vehicle with everything in it, like the coolant, the fuel, and the person who runs it. So these two weights, empty and loaded, are often referred to as the net vehicle weight, or NVW, and the gross vehicle weight, or GVW. Okay. So another important thing to remember is that the horizontal weight data is presented as a log scale. Okay. So this guy, both this and this, both of them are in log scale. Well, it doesn't change the procedure at all. It just tell you know that it is in log scale. So here is just an explanation of what we did in the previous slide. It explains these steps. Okay, so you can read them from the slides later if you're interested, but basically they're just saying what I explained a few minutes ago. Yep. All right, so something funny to take a very quick break. I can actually get out of this window. So this is the window, and if I want, I can get out of it. And you see, I can come out of this chart. Those of you who are good in graphics, can you make a guess how this is possible? Well, that's not a very complicated thing, but just asking. All right, so the last chart, promise this is the last one, is the retarder performance test. So what is a retarder? Let's say you're working with a very heavy equipment and you're going down a hill, okay? So if you do not control the speed of the vehicle, you have to, hit the brake many times. And each one you do this, there will be pressure on the tires. The tires will be worn out, a lot more quickly, and you will have to spend a lot of money on them. They are super expensive, as you know. So you don't want this to happen. That's why you install a device on your machine, which is called a retarder. Then the retarder can control the speed of the vehicle, especially when you're going down a hill. Okay, so it won't allow your vehicle to increase its speed. Okay, so the way we work with it, let me first explain it. Let's just have a review of what I just said. Yeah, steep downgrades. If you want to use the brake, your machine will have a lot of, it will be a lot of pressure on your machine. So you don't want it. That's why you install a retarder, which is a dynamic speed control device. Okay, I got that on my car actually. Well, it's a crossover, but it has it. So anyway, the retarder will not stop the machine. Instead, it provides speed control for long downhill hauls. Yeah, so you won't need to use the brake for that because it won't allow your vehicle to exceed a certain speed that could be identified by the operator. When the magnitude of the grade assistance downward slope is greater than the resisting rolling resistance encountered, then the retarder performance chart identifies the steady speed, okay, a vehicle will maintain while descending. As you can see, there is no ripple here. Oops. There is no ripple here. So there's no information here all the information you need are these guys, depending on how steep is the down. So in fact, these numbers are negative because you would not use a retarder when you're going up. We're working with the negative slope. We're going down a hill. But anyway, we didn't, I mean, the chart does not put minuses or negatives next to these numbers, but keep in mind they are negative slopes. So it's exactly the way we did with the previous chart. You find the corresponding grade and the corresponding diagonal line, and then draw a horizontal line. So let's say if it is, for example, 20%, you draw a you see, and you have the gross weight of the car. Let's say, for example, the gross weight of the car is 80,000 pounds. So if it is 80,000, I'm writing with this device, which is not perfect, but it does the job somehow. Anyway, so 80,000 pounds, you see, it's like a used pen, which I don't know because it's a plastic. Anyway, so 80,000 would fall here, and you have, so you should see this and this, okay. Oh, the way you actually do it is to draw a horizontal line, okay, and then see where it intersects the gears, and then you would draw another vertical line down, so you would find the corresponding speed. Again, it could be either in kilometer per hour or mile per hour, okay? Yeah, you might ask me that when I draw the horizontal line, I could intersect the same gear, let's say it's the fourth gear, I could intersect in two different points, in more than one single point, okay? So we could intersect here, or we could intersect here. Why? Because all of the gears have a shape like this if you look at them, okay? Some of them are like this, some of them are like this, and the horizontal line could intersect in two different points. So which of these two different points should I use? That's funny one. So that's the topic of this slide. Retarder performance chart. So when so the horizontal line can intersect with more than one gear in a particular gear, okay? The vertical portion, what does that mean? The vertical portion, so this is a diagonal portion, this is the vertical portion. So if you rely on the vertical portion, that will give you the maximum retarder effort, okay? So when you are drawing the horizontal line, you will have a vertical portion and you will have a diagonal portion, okay? So the vertical one shows you the maximum retarder effort. Yeah, and yeah, it is also important then that by changing the gears, you can also, you can also change the speed. And as you can see, if you change the speed, if you change the gear, you will have different corresponding speeds. So based on if you need a lower or a higher speed, depending on your machine, because you want to keep your machine for a long time because they're expensive, so you could select accordingly what gear would be the best for the speed you want. All right, that completes this chapter I will be available for questions, comments, concerns, and I hope, I guess this is a very, practical, one of those practical chapters. In fact, all of the chapters we have covered so far are the fundamentals of equipment. And from the next chapter on, we will focus on specific machines like dozers, like graders. And then, so far, whatever we have learned are general, and they could work for a, big variety of different equipment. All right, I hope you all enjoyed the virtual class, and I will see you in the next class. Thank you.